Mic check. Okay, good morning. See a couple of you here. Himanshi, Glazer, good morning. Good morning to everybody else who's here who I can't see in chat or can't see you yet. Good morning, Captain Price. Hopefully everyone's doing well this morning. Probably if you were in programming algorithms too, you had a stressful last 24 hours or so, at least you're past that, and hopefully, as there always hopefully will be, there's technical skills and other lessons to be learned from every experience like that. So anyway, this is the assembly class, so that's something else, but I'm saying that because you guys in your class do have a project coming up. It seems like it's many, many weeks away, but the time to work on it is right now. It's exceedingly difficult to do this, to work on a project early and then improve upon it over time, but if you do that, you leave yourself ample time to get help where or as needed. So keep that in mind. I highly recommend that you start the second individual project. Today is Monday, isn't it? Yeah. Okay, so if you haven't seen it yet, you'll see in every section that I teach, there's a feedback. It's anonymous feedback, but it's your chance to tell me and my supervisors what I can do to be better. So if you have a few moments, please do that. You should see it at the top of your announcements. And it's not from me, it's not initiated by me, and I don't see it except for I see the summary data that's fully anonymized later. So that's what that feedback, the announcement thing is. Okay, we are in week 11. So it sounds scary on paper, addressing mode. So just so you know, be careful when you're reading. Look at the available answers and make sure you're sort of matching up the right answer with the correct concept. You actually know what addressing modes are, especially if you've done, if you're in the second semester of programming at Butte College, then you definitely know what all of the different addressing modes look like, more or less. So anyway, it sounds scary and it sounds fancy. Addressing modes, it's a critical component of any processor model. All it really means is, how do I access information? If I put data in memory, how do I access it? If I create a structure like an array, how do I access the individual elements of the array? And there is a processor component to that. The processor has to provide the functionality that lets you access data in different ways. So that's what this week is about. And just sort of looking ahead, so the second individual project is not due until December 13th. But if you count the fact that the Thanksgiving week is coming up, which for a lot of people is a busy week, if you count the fact that the holiday season kicks up and some of you might get extra work shifts, or you might be doing shopping or preparing for family or whatever it is that you do, please keep those things in mind. Like this week, if you haven't already, is the week to start the second individual project. And get used to the idea that you can engineer a solution in steps. Building a bridge doesn't mean that you have the whole bridge and you plop it down. You have to lay a cornerstone, right? So that's kind of the same idea. Okay, week 11. But anyway, as we're ticking down on the weeks, that feels pretty good. Hopefully you also are feeling good about that, before you know it, we'll be at the end of the semester. Okay, so our goals this week, first is just to get you accustomed to the term addressing mode. What does it mean? I'll just tell you the secret answer is that an addressing mode is simply the different ways that a processor allows you to access information. That's it. Typically we're talking about in RAM when we say that. So how do I get information that I've stored in the computer's memory? And on the x86 there are basically 4 different mechanisms that the processor supports for you doing that. So that's sort of the second one. What are the 4 addressing modes on x86 and how do they work? We're only doing a couple of them this week, and then we'll add more in the coming weeks. So in our HLA programming, we will use the address of operator, which will look very familiar with you if you've done some C++, and also the load effective address instructions so that we can get at the addresses of things in memory. And then we will use direct and indirect. Those are the two that we'll experiment with this week. Direct addressing and indirect addressing, which you're going to see in code, and I think that's the place where you understand it the best. Or at least that's the place where I understand it the best. Hopefully that's true for you too. Okay, so a couple of different sections from the book. So these readings aren't super long, but of course you have those open and use them to attack the homework questions. The lab I will come... Wait, is this the lab? No, that's the homework. I feel like we've been away for a long time. I don't know why. I think it's because I've had a lot of grading, so I've had less time to just imagine my teaching work and more time doing grading source code in the last few days. Okay, so we'll come back to the lab. The Piazza discussion is asking you to sort of think about how do high-level languages translate x86 addressing modes. The most obvious example, and you guys can repeat this in the discussion if you want, but the most obvious example is indexing an array is the one that looks like an addressing mode. But it turns out that every time that you declare a variable in a high-level language, you are using an addressing mode. A pointer in C++ is also using an addressing mode. And then the reminders. So again, it seems like we're far away from the second individual project, but it's HLA and it's going to be mostly assembly style code by the time we're done. So you already know what HLA code looks like, and as it gets bigger and bigger and bigger, it gets scarier and scarier and scarier. So unless you're super confident, you probably don't want to wait until the last day to get this project started. Like, start building it piece by piece as you go. In fact, maybe I'll just sort of show you how I would start it today. Okay, is there anything no, that's it, right? Okay, so I need to adjust my display because I noticed I forgot to put my notes up. So let me put those where you can see them. Okay, so what we're going to look at, and I'm just going to list for you the x86 addressing modes. One is called direct addressing. That's the one that you're most familiar with. In fact, I can probably... Can these things coexist? They can. So let me log in and actually do a little bit of code and show you these addressing modes as I go. Okay, so program, make sure I get it in the right place, and also switch it. Okay. Just looking to see who's here. So if I didn't say good morning to you, good morning. Captain Price, Glazer, Gersovax, Hamanchi, Tyler, good morning. Okay, so we have direct addressing mode. So what does a direct addressing mode mean and what does it look like? So remember, the whole idea of addressing modes is if you put data in memory, how do you access it later? So let's make a variable. I'll just call it x, and I'll make it an int 8 just for fun. So when you declare static in HLA, that goes in RAM. So you're actually using the computer's RAM, not the processor's registers, of course, in this case. And x86 allows what's called direct addressing. And what direct addressing means is you list the variable's name and you directly manipulate its data. So if I were to say move 42, I'll use 99, I'll use negative 99 to x. So this is direct addressing. Wherever in RAM x is, I don't have to worry about it. Okay, I'll get to that in just a second, Captain Price. So direct addressing mode means that as the programmer, I don't have to worry about where in RAM that x is. I just use the label for it, and basically the computer and the software take me directly to that location in RAM. So that's what direct addressing looks like. It also looks like this, by the way. So here again, I've used x to directly access the value in a location in memory. So that's what direct addressing looks like. You can. So, and then I'll get back to your other question, Captain Price. So one question is, can we read the address? Can we get the address of x? And we can, and we're going to do that here right after this. So I'll answer that in code. So yes, we can actually get the actual address in RAM. So every variable we create has an address in memory, and we can get that address and we can use that address to go to that same location in memory. Now there's another question. So how much RAM can you allocate with HLA? That's actually, so technically we are doing 32-bit. x86 programming, so we can access as much RAM as 2 to the 31st will go. So when you're in 32-bit, you can actually address up to 2 to the 31st addresses in RAM. Now some of that RAM you won't be able to access because the processor and the operating system are keeping you away from it, but technically you can access 32 bits of memory addresses in RAM, which is a lot. Yeah, roughly 4 gigs is, so 32 bits will get you 4 gigs of RAM that you can directly address. Okay, so that's good. Yeah, so, and then Captain Price's follow-up question, so can we get the address of X? We can. Can we use the address to actually access memory? And we can, and let's do that. Okay, so this is direct addressing. It's what you're used to until you get into the second half of programming algorithms 2. Now technically this is not the case, but the way you have experienced programming, most of you up to now, you create a variable or you create an object and then you go directly to the data that's associated with that thing in RAM. That's direct addressing. So now let's add indirect addressing. Oh, and by the way, you'll see that there are some alternate terms being used for direct addressing. So in some places they will call that displacement only addressing. I don't like that term because it doesn't speak to me. In fact, I find it confusing. It's direct addressing. That's in my opinion, the easier way to remember how this works. Okay, so now let's do indirect addressing. So indirect addressing is what you do in the old days when you looked up a business in the phone book. So you'd look them up in the phone book, you would get their address, and then you would drive to that address. That's indirect addressing, having to go to the phone book first and then use the address you find in the phone book to go find the business or the person. That's indirect addressing. So you have to get the address first, and then you use the address to get to the thing that you're actually interested in. Yes, so Cadden Price asked, do hard drives use addresses? And they do. So basically every kind of storage medium that you use, the data on it is accessed through some kind of address. So that's true. Okay, so indirect addressing mode is using the address of a thing instead of the thing itself to access the data. So I'm actually going to put a line of code here to set up for this. So I would not call what I'm doing here indirect addressing yet. This is just kind of setting up for indirect addressing. But what I've done here is I've used the ampersand, same thing as in C++, by the way, and C. So the ampersand in front of X says I don't want the data at X, I want X's address in memory. And I'm going to put that in EAX. Now why EAX? You can load addresses onto the stack, yes, because they're 32 bits. Okay, so the reason why we're taking the address of X and copying it into EAX is because in HLA, all addresses are 32 bits. So if I'm going to get the address of something, it has to go somewhere that's 32 bits. On your modern computer, like the one I'm using and probably the one you're using, those are 64-bit computers, which means that the addresses are 64 bits. And all that really means is you have a lot larger range of addresses that you can use, which means you can have more RAM because you can address more RAM. Anyway, so taking the address of X and moving it into EAX. Why EAX? Because all addresses in HLA are 32 bits. So wherever I take an address, I have to put it somewhere that can hold 32 bits. Now this is weird because X by itself is only 8 bits, and the address of X is 32 bits. And you just have to keep those things straight. In fact, I'll put that in my notes here. So all addresses in HLA are 32 bits, all of them. It does not matter what kind of variable it is. If it's an int 8, its address is 32 bits. If it's a char, its address is 32 bits. If it's an uns32, its address is 32 bits. All addresses in HLA are 32 bits. It doesn't matter at all what the underlying data type is. So X actually uses less space to store the data than its address is, right? It's only 8 bits worth of storage, but the address to get to those 8 bits is 32 bits. And that just feels weird, but that just is what it is. Notice again, I'm not quite ready for doing indirect addressing. This is the setup part. So I'm going to take the address of X. X is an int 8, but it doesn't matter. Everything has a 32-bit address, and put it in EAX. I could put it in EBX, I could put it in ECX, I could put it in EDX. Doesn't really matter as long as it's 32 bits because it's an address. Yeah, that's true. So Captain Price points out, if I were on a system that were using 64-bit addresses, the amount that it scales is an incredible amount. It goes from 4 gigs roughly to 2 terabytes of addressable space. It's pretty danged amazing. And no doubt we'll figure out a way to use all that address space, and then we'll need 128-bit or something else. Okay, so still setting up to do indirect addressing. We're not doing it yet. Let's look at what the address looks like. I'm going to put a $sign because this is going to be hex. So EAX has the address of X in it. Let's run that just to see what it looks like. I should see negative 99, and then I should see wherever it is in RAM, roughly. So the question is, does the ampersand mean pointer to? And yeah, that's how we use the term pointer. Although in this class, I would probably favor the term address of. So the ampersand gets us the address of a variable. You can only use it with statics, by the way. But knowing that pointers are just addresses, yes. EAX is effectively a pointer to a memory location, yeah. Okay, so let's look at its address just for fun. That address, I have no control over that. That is entirely a matter of where the operating system decided to allocate memory for my program as it's running. But that is in the computer's RAM where that variable lives. If I go to that address and I look at 8 bits of data, I will find negative 99, or at least the bits that mean negative 99. Okay, now let's do some indirect addressing. So the whole point of indirect addressing is it allows you to access RAM through addresses. And the way you do that we're going to do a couple of different things. So actually, let's change it first. Let's do the easy one first. Okay, so direct addressing is you just use the variable's name, boom, you got the value. That's what we've done up here. Boom, you access the in this case for overwriting it, in this case for fetching the current value of it. Okay, so indirect addressing, what that means is that you have an address and you have to use it to get to the memory location that the address is referring to or pointing to, which is why we use the term pointer. Where does that address point to? Okay, so let's do that. Do I want to do it this way? Sure. Let's do a simple one first. Okay, so the square brackets in fact, I don't know why I quoted that. In HLA, the way that you dereference a memory address, which is to say take the address and go to where it refers to, in HLA, dereferencing is accomplished by square brackets. So this is a little bit different because you're used to the square brackets meaning array probably. But in HLA, the square brackets mean go to that, take that address and go to the memory location that it refers to. Yes, so I haven't finished the line, but good catch, Captain Price. I still owe it some code. Okay, so on the left side, all I've done is I've dereferenced an address. I'm saying I don't care about the address, I care about the memory, the RAM that it's referring to. So if I put the square brackets around it, I am going there. And in a move instruction, what this really will be interpreted as is go to that address and get the value there. Not the address, but the value at that address. The second argument has to match how much data you want to get. So if I go to this address, which is the address of X, knowing that X is 8 bits, when I go to this address, I want to get 8 bits. And the way I can make HLA do that is simply by telling it to put it in an 8-bit location. Oh, I didn't see that. If you see typos in the labs, I would love to hear about it, so I can fix those. I'll try to remember. If you know what line number that was on, could you tell me what that was so I can go fix it? Okay, so go to the address that's EAX, dereference it, which means get the value there, and then HLA is going to match up how much data to get from here based on where it's supposed to put it. So if HLA is told I need to copy some data into BL, then HLA knows, oh, I need to get 8 bits to do that. Then we can this, by the way, is direct. Can be pretty confusing at first. So I use indirect addressing to dereference an address and get 8 bits of data out of it. Now, since the address is of an 8-bit variable, if I go to that address and get 8 bits, then I'm going to get the value associated with that variable, which in this case is the value of x. So, pardon me. Because I now have it in a register, I need to dereference it. So what I should see here is that the value in BL, typecast to be an int 8, to match x, should be the original negative 99. So there's the original negative 99 that I went and I used indirect addressing to get that value. Okay, so now let's do so we didn't actually need BL at the end of the day. We can just dereference directly and then use a typecast to get 8 bits and get the same result. So same thing, if we dereference EAX, that's the address of x, and if we typecast that to be int 8, then we're going to get the 8 bits that are the actual original x. So still negative 99 because I'm still at, no problem, Captain Price. So anyway, I guess maybe there wasn't a typo, but no problem. I mean, if you think there might be, I would much rather just make sure that I'm perfect on my end. So way better to just say you think you found one, and then we go explore it, and if we find one, then I fix it, and if we don't, then all's good. So no problem. Okay, so this is indirect. So how do I know it's indirect? Because of the square brackets and a 32-bit register. That's how I know it's indirect. Something 32 bits, because we're in HLA, inside of square brackets tells me that's indirect addressing. That is the address of something in RAM being dereferenced to get at the actual original data, and then something being done with it. We can also use it like this. So we can say move, let's say, I don't know, 33. Now this one's going to look confusing because you haven't seen this setup before. So you sort of have to reason out, why would I do it this way? So the value 33, the decimal value 33 in HLA, it can be represented as an 8-bit value, or it can be represented as a 16-bit value, or it can be represented as a 32-bit value. It's just a matter of how many zeros that are getting padded. But HLA doesn't necessarily know, going from left to right, how many bits I mean to consume. So what I have to do is tell it, I want to put this into this memory location, interpret it as an int 8. It's kind of weird, but the point kind of is, if you're in doubt, I'm short of parentheses. If you're in doubt, then typecast when you're doing indirect addressing to be sure that you're getting the right amount of data. So address is always 32 bits. The amount of data at the address can change, which is why we often are using typecasting so that HLA knows how much data to affect. We take the binary of 33, and we tell HLA to put it at that RAM location as an int 8. Now, we'll revert to direct addressing, and then I'll make this a little one-off quiz question. So what is that last output? What's going to be that last output? X equals 33, a great one, Glazer. So this is pretty roundabout stuff, isn't it? But since I moved 33 as an int 8 into this RAM location, and this RAM location is the same location that X directly refers to, then printing out X in the end should give me the last piece of data that I put there, which was that 33. Let's confirm that that's the case. So there's the 33, which is pretty awesome. Okay, so we have two addressing modes here. We have direct addressing mode, which is the thing is the data. So in this case, for example, X is the data, and you just use X to change the data or to print the data or whatever it is. Then you have indirect addressing, where you have an address that you have to dereference to get at the data. The tricky part here is knowing when and when not to typecast. So I will just tell you, for example, on line 19, I did not use a typecast because I know how HLA works from having used it for a while. But if you're in doubt, then just typecast. So it's always best, when in doubt, to just make sure HLA knows precisely how much data you need at the address, right? So in this case, I need an int 8's worth of data from this address, and it works just the same. So it doesn't affect anything. So when in doubt, with indirect addressing, typecast. No. When in doubt, when you're doing indirect addressing, typecast. So that's some pretty crazy stuff. I'm going to move this to the side and make a slightly cleaner one of it. Do I need that yet? Probably not. Okay, so direct. The thing is the data, right? So direct addressing with X. X is the data. It's the data when I want to change it. It's the data when I want to access it or print it or view it or use it or whatever it is. Indirect addressing, you have to have an address and then dereference it to get the data. So indirect addressing means that you have an address that has to be dereferenced to change the data, to view the data, to copy the data, whatever it is, you have to dereference it. So if you see the square brackets, you are looking at some form of indirect addressing. And that's the only two that we need this week, and then we can yeah, we're doing okay on time, so we can proceed to the lab stuff. One more thing about all this. Let's make it crazy. All right, so I'm going to move move this code down to the bottom. In fact, I'm going to move it off to the side for a second. So I can make a clean one. So what I'm just going to do a little bit more of exploring of what indirect addressing means. So in HLA, which is a reflection of what the x86 processor can do, in HLA, if you want to store an address in memory, then you would use a 32-bit data type. I typically use dword, which just means raw 32 bits of data. So when I want to store the address of a thing, I will usually declare a dword variable, which is 32 bits, to hold that address. Dword just means 32 bits with no specific data type. So not a 32-bit unsigned integer, not a 32-bit signed integer. This is just 32 bits of the data type don't matter because it's just an address. Okay, but I want to show you that all addresses are 32 bits. So if I were to do this, the address of x into adder. I'm actually going to write a procedure to do this just to make it more interesting. Do I want to do that yet? No, let's not do that. Okay, so you can store the addresses of things for the long term. This is like declaring an array in C++ or some other high-level language, or like declaring a pointer in a high-level language like C or C++. Sometimes you need a variable whose job is to store an address of a thing for the long term, typically because you want to be able to get back to that address later. But I want to show you how we can use variables to store addresses and then what the implications of that are. So I can move the addresses of stuff. I am going to write a procedure, I decided. I'll just call it use an address. I'm going to, I need an address here. If you are in PNA 2 right now, then all this addresses of stuff, this is pointers. As Captain Price pointed out, this is what they look like in assembly roughly versus a pointer in C++. Okay, so we can actually pass an address to a procedure, and then we can use the address to mess with the original data. So I can take that address and I can say, now one thing you can't do is you can't use the address variable directly. So you have to put it into a register before you can dereference it. So you have to do indirect addressing out of a register. So EAX, the middleman, and then I will put some data there. Let's just say 10. Okay, so that procedure, what it's going to do is it's going to receive an address. It's going to load that address into a register so that it's usable. And then it's going to dereference that register, do indirect addressing, to load some data in there. So notice here, the reason why I typecast int 8 is because I know that what I'm using right now is x, which is an int 8. So that's why I did that. But if we were to output, so I'll pass that address to the procedure and then have the procedure do something. If I were to output x right now, probably you know what is about to happen. So does anyone want to venture a guess as to what x is going to be here? $10. Good one, Glazer. At least it better be. Good one, Tyler. Yes. Let's hope. Because it's supposed to be. So x is 10. So that's as expected. Okay. Now we're going to use it again. And I'm hoping also that you'll see why I've done in the lab what I've done. So let's move the address of y in there. Now, the reason why this works is because even though y is a different data type, the amount of data is different, the size of the address isn't. So everything has a 32-bit address, so any static variable can have its address loaded into this variable. Anyone, it doesn't matter. But we do get to a problem here. Well, let's just see what happens if we run it. Okay, they're both 10, so far they're working. But let's mess with it a little bit. Let's put a large value in here, like, oh, I don't know, 128. I don't know, wait, what just happened? My num lock was off. Alright, so I'm going to put 128 in here. So there is a problem with 128. Int 8s can't hold 128. Int 8s can only hold up to 127. So this use address breaks if the incoming address is the wrong kind of data. Hopefully that makes sense. As soon as I change this to something that X can't be, then X shows a wrong result. Y worked because it fit, but X didn't. So how do we address this problem? What we need to be able to do is tell the procedure how much data we're talking about here. So that the procedure knows how big to typecast to. So the way I do that is I add a parameter here. I'll call it the D type, and I will make it an uns8. Doesn't really matter what it is. But it's a parameter that the procedure can then use to decide. The size of it, by the way, doesn't matter. But the procedure can use this to decide how big of a typecast to do, or how small of one. So we could say, for example, if the data type that's coming in alongside that address is a data type 1, made it up, doesn't matter, then we'll load up, let's just say, let's do the max value here. No, I don't want to do that. Let's just say 10. Then we're going to type to int 8. Or if the address comes in alongside a D type of 2, then maybe we'll load up a much larger value, and we'll typecast to int16 instead. Or let's go ahead and allow for this uns32, which I'm going to call a data type 30 just for fun. 35, I think it'll go. Now I hope I didn't lose you. This D type, I'm just making it up as I go along. I just decided, oh, D type 1 means typecast to int 8. But that also means I can't move anything that wouldn't fit in int 8. D type 2, just made it up. I decided, okay, well in that case I'll typecast int 16, and I'll load up a value that is appropriately sized for that. A D type of 30, just made it up. I'll move something that would be appropriate for an uns32 and typecast to that. So the processor doesn't care where the address goes. It's your job to make sure that it goes to the right place and matches the kind of data that you're working with there. My whole thing that I had in my head, by the way, is like 1, 2, and 3 would be int 8, int 16, int 32, and 10, 20, and 30 could be uns8, uns16, uns32, so like my little coding system. That's all that means. So when I call that, I can then tell the procedure, hey, this one needs to be typecast to int 8, and hey, this one needs to be typecast to int 16, and then I'll do the last one. And then I'll tell the procedure, hey, this one needs to be typecast to uns32 to work correctly. Now I did that in part just to, so that you're prepared for what's coming on the lab, but also to show you that an address is an address and is an address until in code you tie it down to the actual size and type of data that you want it to be with the typecast. So there's my data all loaded up like I expected it to be. Okay, how are we on time? Still doing okay on time. I'll also just go do a quick review thing. So line 14, actually, let's see if we can get a few of you guys to weigh in on this. So remember, if there's square brackets, it is indirect addressing. If there's no square brackets, then it is direct addressing. So line 14, direct or indirect? Direct, good one. No square brackets. So it's just taking directly from memory some value and putting it in EAX. Now we happen to know that what's in there is an address of something else, but as it is, it's an address being stored in memory. Kind of weird, right? You have an address to get to a location in memory, and then at that location is an address of something else. Seems kind of complicated, but there's no square brackets, so it must be direct addressing. What about line 16, direct or indirect? Indirect. Good one, Glazer. The square brackets tell you, oh, they're actually using an address to go to a location in memory, dereferencing an address to get at a location in memory. 18, direct or indirect? Indirect, good one. So I'll do one more, which I'll just pick one. Line 37, direct or indirect? It's direct. Good one. Perfect. Tyler and Glazer right on top of it. There's no square brackets, it's just direct. Okay. So the square brackets is the tell. That's indirect addressing, and what that means is, oh, there's an address here, and someone is taking that address and going to get data at that memory location that the address refers to. All right, last thing before we look at the lab. This move address of X to ADDR, that address of operator only works for static variables, which is fine, but I want to show you an alternative to it. So when you have a static variable, it's very simple to go get its address with address of. But you can also, and this one looks funny because it's backwards, you can also use an instruction that means load effective address. And this is the one instruction that I can think of right now that's backwards. I don't know why it's backwards, but it's backwards. So what LEA does, load effective address, it takes the address of the right-hand thing and loads it into the left-hand thing. I don't know why this one's backwards. I feel like it was a mistake when Randall Hyde was making HLA, but there may be a reason that he does it this way. So it's backwards. But it has the same effect as the move above it. It takes the address of X and loads it into that variable. So we can use that on all of them as an alternative. For now, I just want you to know that it exists. We don't need it for the time being, although you do need it for the lab because I asked you to use it. So this is an alternative for getting the address of a thing. What's weird about it is that it's backwards. Unlike all the rest that go left to right, this one goes right to left. I have no idea why, but it does. Somewhere I messed up. That should have worked. Line 28. What did I do wrong with it? Oh. My guess is you have to put it into a register. I didn't do the one for Z backwards. You're correct. Although maybe I have to use a register for this. Yep. I bet you I have to use a register. Let's see. I should get errors in a different location if that's correct. Yep. So you actually have to load effective address into a register first. And then copy it over into a variable for long-term storage. There's something about the work the computer has to do here, by the way, so I know that this one, although I'll confirm that, the error should move down to line 40 now. So load effective address will not work on a static variable. You have to put it into a register. But good catch, Glazer, on the backwards one. I did have that Z one backwards. Which means I had it the right way, but the wrong way for HLA. So load effective address of Z into a register and then copy that over into my variable. Technically, I don't actually need those variables anymore. Just going to make sure the data still looks good. Okay. So this load effective address is an alternative way of getting the address of a thing. We don't need it yet, but it turns out that this ampersand style of getting an address only works for statically declared things. Later in the semester, we're going to have dynamically declared things, and then we're probably going to need load effective address at some point. But anyway, this is an alternative for getting the address of a thing to the address of a symbol in HLA. Okay, there's that thing. Let's close that. I'll just move it to the side. So let me know if I forget to switch the display back. But what I'm about to do is go grab the lab code and let's just go explore it to get you off on the right foot with it. Now, I happen to think that this address stuff is just kind of cool. And what I hope that you find, especially if you're currently in a C++ class, that this is kind of reinforcing the underlying concept of what does a pointer mean and what do the keywords new and delete mean, because you're about to have all that experience at the processor level. So this is what is actually happening when you make a pointer in C++, is that you are setting up to do indirect addressing on the processor. This is the lab code. Get the raw version. Can you see what I'm doing? Yeah. So I'm going to get the lab code, and then we'll just go down through it a little bit together to make sure that you're off to a good start. So I'm going to copy that. I'm going to switch my display back, and then I'm going to fire up a new file here. I'm going to call it lab 11. Lab 11. Pretty good. Make sure it goes in the right place. And then get some things where we can see what we're doing. Okay, so lab 11. So you're going to see at this point that we have 3 different get int procedures. We have a get int 8 procedure, we have a get int 16 procedure, and we have a get int 32 procedure. The 32 and the 16-bit ones need to be implemented by us. The reason why you have all 3 of these is because it makes the second project a lot easier if you have all 3 of these get int procedures separate. That way you do the appropriate get I8, get I16, get I32. You have the ability to limit the inputs to between a minimum and a maximum of the appropriate data type. It's just how I went about doing my individual project too. So what I'm giving you in these 3 procedures is procedures that I used in my implementation of the second individual project. I found it useful to just have all three of them there, and then whenever I need an 8-bit one, I call for that. Whenever I need a 16-bit one, I call for that. And whenever I need a 32-bit one, I call for that. It just made life a lot easier. So I'm sharing the idea with you, and those are great things that you could have in your second individual project. This first one is done. So I'm going to handwrite the second one just to talk through it, but your job is to do a get int 16 version of that. So here's how we set up to do robust input handling. We're going to put it in a forever loop. And the idea here is that we're not letting them leave forever until we get an int 16 and an int 16 that's in the proper range. So forever they're going to be here doing this. Okay, so what's the process then? I'm kind of make sure I do it more or less the same way. The first thing we're going to do is we're going to output the prompt. So that the prompt is parameterized means that we can change what the prompt says. So please enter a menu selection could be the prompt, or please enter new data for this variable could be the prompt. This makes it so we can use these procedures in more context simply by parameterizing the prompt. So now it can be customized for the current situation. Okay, now what we do is we enter into the try loop, or the try block. I'll space it out so you can see better. No. Okay, so the meat of this algorithm is really in this try exception block. So we're going to use this to both detect when they've been an idiot and typed something that's too big or too small for int 16, or they typed hello when I wanted a number. We're going to detect that in here. And we're also going to use this to enforce our range. So the first thing we're going to do is try to get a signed 16-bit integer. Now, if anything goes wrong, this is the point where if they're typing something and it's just not even possible that it could be an integer 16, the program's going to pop down into this section right here. So if anything goes wrong here, the program's immediately going to jump to the exception part. And if that happens, then we know they did something wrong, and we can say, I'm going to use a similar, not a valid 16-bit integer. I'm just going to use the same words. Did I use 2 new lines? I did. Whoa! Sorry. So that's my first thing that I do is I do the meat, which is try to get a number, and then I handle the exception, which would be, hey, whatever it is that you typed in wasn't even an int 16. It doesn't even matter if it's in the range anymore because it's not even legally an int 16. Okay, so that's that part. Now, if we go back up to here, if the program manages to flow to the next line below the get I16, then what they typed is legitimately an int 16. So if the program can flow to this line right here, then what they typed is at least an int 16. So at this stage is where I can enforce my range, because just because it's an int 16 doesn't mean it's in the range that I wanted. So I'm going to do my check. So I'm going to break, and this break will break the nearest loop. So as soon as I get a legitimate 16, then I will see if it's okay for me to break if AX, their input, is greater than or equal to the min, and AX is less than or equal to the max. And I'll show you that I sometimes have a little bit of paranoia about this. You can see where I typecast. I never remember for sure if HLA is smart enough to know that it should make that into an int 16. So when in doubt, typecast. Like, I want to be sure that HLA remembers AX is supposed to be int 16 here, so I'm going to typecast it. And I'm going to do the same thing over here. In the context of the comparison. So remember, this is direct addressing, so this is like at the point where it gets really confusing. When they do a get I16, the actual value they typed goes in a register. So we use direct addressing to get to the actual value they typed that's stored in that register. And the reason why I'm typecasting here is in part to get you in the habit to think, when in doubt, typecast. When in doubt, typecast. So I'm going to make sure that HLA knows that AX has an int 16 in it for the purposes of comparing with that int 16. Same thing on the right. Make sure that HLA knows AX is an int 16. Now if I don't break, then I get here. Oh, I forgot unprotected. No one caught me. What is all that? Okay. You need this because if you don't do it, you're going to have weird bugs. It's a weird HLA thing. So just make sure that once you successfully get an I16, I probably did a flush input as well. I did. Let's do a flush input. Let's break out if we are within the desired range. Now if we don't break, then we're going to be here, and it's time for them to get a nastygram. How to input is not between. Okay. And why not use our parameters to make fancier output? So if they didn't break, that means they did type in a legitimate int 16, but it wasn't in the desired range, so they get a nastygram that will tell them your input is not between my two parameters. And then the loop will continue, and they'll get the prompt again, and then they'll try to do the input again. So I don't know if that helped, but I tried to sort of talk you through the whole thing. You're going to do one for yourself on the int 32. It's going to look just like this, but adjusted because you're going to be doing 32-bit stuff and not 16-bit stuff. Once you've done that, you have the full complement of input handling that you need, in my opinion, for the second individual project. Okay, let's see what else is going on in here. So step 2 is to do the int 32 for yourself. Go again's already been done. Okay, here's number 3. So here's that same kind of setup that I exposed you to in my little sample. We're being given an address, and then we're being given a code that tells us which typecasting we should be doing. And here's the key, right? So if that I type is a 1, I'm supposed to typecast to int 8. If the I type is 2, I'm supposed to typecast to int 16. If I type is 3, I'm supposed to typecast to int 32. Those codes, 1, 2, and 3, I totally made them up. But I've already also set up code to be prepared for those. So number 3. I can kind of use this, but let's do it from scratch. Are we doing okay on time? Probably. Okay, so this will be the last one, I think. So hopefully you're used to this. I usually will give you at least one example that's similar, and then you have to make an adjustment. So in this case, I type is 2 means that my typecasts need to be for int 16s. Okay, so what's the process? I need to dereference the address and move it into something that's 16-bit. BX would be 16 bits. When in doubt, typecast. In this case, it doesn't actually matter, but when in doubt, just do it. Just typecast. All right, so now I have in BX, yes, 32. Good catch. I need to go fix that as soon as we get done here. Good catch, Tyler. Thank you. Yeah, that's int 32. So number 4 is int 32. In fact, I'll just go fix it real quick. I'm not logged in. It's not going to work out. I'll have to fix it right after I finish lecture. So anyway, if you already have the code, that last one is int 32, but I'm going to go fix it as soon as I stop talking. Okay, so number 3, the address, this time I know I'm supposed to do int 16 stuff, so I need 16-bit things, whereas above here they use BL because it was int 8 or 8 bits. Now it's int 16 or 16 bits, and this last one, thanks to Tyler fixing it, will be int 32 or 32 bits, and then you do an output here. Typecast int 16, that's not going to work obviously, but int 16. Hopefully you get the idea. And let's see what else is left that I can give you tips about. So then you have number 4, that'll be the 32-bit version of that. And then number 5 is going to be a get int 16. And one thing that you might do to make this more interesting is simply, so there's my prompt that the procedure will use to spit that out, and then I'll put, and then that way, if I put numbers that are impossible for int 8, then I'm at least kind of might catch with a compiler error or a bug with those values. So I adjusted the values up for int 16. And then I know that get I16 should bring me back AX with the input, and then I will put that in the num16 variable, and then we're ready to go. So you're going to do a 32-bit one of those. Okay, addresses. So number 7, copy the address of num16. So notice again, there's an example for the num8. So we load the address of num8 into EAX, and then we call print value with that address and code 1 because it's int 8. So on the second one, you're going to do a move, and you're going to call print value but with a code 2, and then the third one will be a code 3. And then the last ones are based on this model, right? So this is just practicing with load effective address. Remember, it's backwards. So you have an example of the num8, and then you'll repeat that for num16 and num32. Okay, I need to stop. I've chewed up a good portion of your day. Thank you, Tyler, for finding that bug, and I'm going to go fix that, and I'll upload a fix to that code immediately into GitHub, so that will show and people won't get confused on that. Okay, that's it. I hope you have a great week. I'll wait around a couple seconds, see if there's any questions. Please think about starting individual project 2. You're not going to be able to do very much, but you can start to sort of build out a project 2 file. I personally found get int 8, get int 16, get int 32 to be useful in my project 2 implementation. So I'm sort of giving those to you through this lab. And I recommend that you start building it out. You can't do much with the main body of the program, but you can do some minimal outputs just to sort of get something that does a little something. And then you should be ready every week to be adding more stuff. So heads up about that. The next several weeks we're going to be adding a little bit, a little bit, and a little bit to build out project 2. Okay, now I'm done. Thanks for being here if you were able to be here this morning. If you're watching later, I hope that your week is great up to that point and great afterwards. Otherwise, I'll see all of you on Monday next week, which will be week 12. Yeah, so have a good day.